Good morning, everyone. Welcome to our keynote session. This morning, just a bit of quick logistics. We'll have the keynote and then the award ceremonies this morning. To get started, let's think about government investment in research. It has been a major driver of innovation and transformative technology, really. There's a government agency in the US that I can say with confidence that if it wasn't because of its innovations, we wouldn't be here today. Inventions that not only transformed the US, but the whole world. Inventions such as the internet, the graphical user interface, the predecessor to the global positioning system, GPS, voice-based personal assistant technology that later became Siri, autonomous vehicles, and many others. This government agency is the Defense Advanced Research Project Agency, or DARPA. It is my distinct honor today to introduce our keynote speaker, Dr. Kathleen Fisher, the Director of Information Innovation Office at DARPA. Dr. Fisher perhaps needs no introduction. She was a luminary member of our community even before her tours at DARPA, but perhaps this introduction is for younger members of our community who may not know her. Dr. Fisher has served as the director of DARPA's Information Innovation Office, I2O, since May 2022, leading efforts to develop technologies ensuring an information advantage for the US and its allies. Previously, she was I2O's deputy director from 2021 to 2022, and a program manager from 2011 to 2014. Before DARPA, Dr. Fisher chaired Tufts University's Computer Science Department from 2016 to 2021 and was a principal technical staff member at AT&T Labs. Dr. Fisher holds a PhD in computer science from Stanford University and has served on the board of trustees at Harvey Mudd College. Today, she's going to talk about resilient systems in an increasingly hostile world. Without further ado, Dr. Kathleen Fisher.
Lead them to focus on resiliency in addition to efficiency. Also, other kinds of trends allowed us to create global supply chains. And then computer science advances and advances in other kinds of technology allowed us to build hyper-complex systems, mega-complex systems, by which I mean systems that are so complex that they don't actually have a single owner that is responsible. So they turn out to be really very difficult to manage. That hyper-focus on efficiency may be the right trade-off in a benevolent world, the way the world has largely appeared from a certain point of view at a certain point in time. That time is over. As COVID pointed out to us, COVID may be largely under control at this point, but we do have a bird flu that is running rampant in the bird population and some of the cattle population right now in the United States. Luckily, it hasn't jumped to humans at the moment very much. Hopefully it won't, but it is wreaking havoc with the price of eggs. So we have to worry about global pandemics. We also have to worry about natural disasters and increases in the rate of natural disasters. In the past year, the city of Haokou in China saw the second most powerful super typhoon in history, we saw a Category 4 type hurricane cause massive flooding in the mountains of North Carolina and Tennessee. And 2 weeks later, another massive hurricane hit the state of Florida. We saw fires just in January consume a large portion of Los Angeles. In fact, 90 square miles were burned and 18,000 structures were destroyed. Those, of course, are just anecdotes, and that could just be, happenstance. But the graphs on this chart show that data that, in fact, it isn't just points in time or individual stories, but in fact, a real trend. The two charts, the one on the left and one on the right, show the number of billion-dollar disasters and the cumulative cost of billion-dollar disasters over two different 20-year periods. The red is from 1983 to 2002. The blue is from 2003 to 2022, so two consecutive 20-year periods, with the blue showing significantly more and significantly higher cost. So we have to worry about increasing numbers and severity of billion-dollar natural disasters. So the natural world is more dangerous. And then we also live in a world of increasing armed conflicts. So the data here is collected by ACLID, which is the Armed Conflict Location and Event Data Initiative. Their data that they've collected from around the world show that global conflicts have doubled over the past 5 years, and that we have extreme, what is the yellow color there? It is, high or extremely high levels of armed conflict on 5 different continents in the past year. Basically, only Australia and Antarctica don't have extreme or very high levels of armed conflict, and the rate is going up. So we have to worry about pandemics, we have to worry about natural disasters, and we have to worry about armed conflict, all of which are significantly increasing in time. And we have to worry about those things in the context of these mega complex systems that I'm talking about, where there is no single owner, and the repercussions of a failure have widespread consequences. So this chart shows 6 different examples. I'm just going to talk about 2 of them. So first, the Texas power crisis that happened in 2021. So if you don't know about the power grids have to exactly balance the amount of power that is being created and the amount of power that is being consumed pretty much at all times, which is like a Herculean feat. And in 2021, that was close to not happening. Because they had an extreme weather event, it became very, very cold in Texas, which happens every once in a while, even though Texas seems to be very south and very hot. Sometimes it gets very, very cold in Texas. And that's very coldness caused simultaneously a spike in demand because Texas uses electricity for heat. So all of the houses turned on their heating system at the same time. And a crash in supply because the coldness caused wind turbines to freeze and stop being able to spin. Texas actually has a large supply of alternate power supplies, which is good for them. So the wind power supply went very far down. Also, they have a number of power generators supplied by natural gas, and the pipe supplying the natural gas froze. So a lot of those power generators went offline at the same time. So demand spiked and supply crashed. And so their ability to match supply and demand went offline, basically. And so the system that manages the power grid started to basically cause blackouts to lower demand even further to match the lowered ability to supply power. But even that causing blackouts wasn't causing the match of supply and demand fast enough, which triggered this countdown, a 9-minute countdown, to shut down the entire power grid. And why is that important? If the supply and demand don't match, causing the sagging supply, then you can destroy the generators and the transformers in the system. And if you destroy that equipment, there's a 2 to 3 year lag in the ability to replace that equipment. So if you destroy that equipment, then your grid is offline for 2 to 3 years. So the 9-minute countdown started. And the 4 minutes and 37 seconds on the screen is how far that countdown got. So they were 4 minutes and 37 seconds from shutting down the entire Texas power grid. If you get to the point of shutting down the power grid, it takes weeks to restart it. So Texas was 4 minutes and 37 seconds away from weeks of no power. Can you imagine what would happen if Texas had no power for weeks? I mean, that's so you wouldn't have years without power, but either way, it would have been a societal disaster, right? So that's an example of a mega complex system failing because of a confluence of a whole bunch of different events, with a system not having sufficient resilience in the system. Another example is the CrowdStrike problem that happened in 2024, last year, that caused, Delta Airlines ended up canceling 7,000 flights over a 5-day period. That was just one of the many airlines. It was the most affected airline. But there were also healthcare providers that were affected. There were payment systems that were affected. There were government industry that was affected. Like, basically, it was very, widespread affected across many, many different industries. Why were these industries affected? Well, there was a blue screen of death problem in many, many different Windows systems. Why were these blue screens of death happening? Well, it was because of a problem in the CrowdStrike software security system, which is monitoring Windows systems for software intrusions to provide recovery systems. The CrowdStrike Falcon product runs in privileged mode. It is constantly getting updates to look for new kinds of vulnerabilities. In their configuration file number 291 got an update. That update supplied 20 fields in a place that was expecting 21 fields. There was an array bounds check that wasn't there, that was missing. It was a file parsing error. It's computer science 101 problems, right? Parsing errors, array bounds checks errors, that led to a crash, a system crash, that was during the boot sequence. And so fixing the problem was really, really painful because it failed during boot sequences that caused a boot loop failure, right? So fixing it was a pain in the neck. And that simple parsing mistake with an array bounds check missing took down Delta Airlines for 5 days. Right? This is the kind of mega complex system failure. So the much more hostile world with pandemics, with natural disasters, with conflicts and war, causing problems with these very complex systems. Those are all natural disasters. We also have hackers that are not just, that can push the systems into these kinds of failures. To give some examples of the kinds of things that hackers can do, I want to talk about the 2017 NotPetya attack. So the GRU, which is a branch of the Russian intelligence, launched an attack on the Ukrainian power grid, but it escaped from its intended audience and ended up attacking Maersk, which is one of the largest shipping conglomerates in the world. It is responsible for about 20% of the world's shipping. This attack ended up destroying 50,000 of Maersk's computers and its VoIP telephone system in about 7 minutes. So way too fast for people to be able to defend against. It destroyed all but one copy of Maersk's Active Directory system, which is the database that they use to keep track of where all of their containers were and what was in all of their containers. So basically, run their business. And the only reason it didn't destroy all copies of their Active Directory system was because there happened to be a power outage in Nigeria. Really, you can't make this stuff up, right? So in this case, a natural disaster or power system failure saved them from having to completely reconstruct their database. So they had to fly somebody down to get the copy of Active Directory from Nigeria and fly it back and use it to reconstruct their database. It was a week before they had any kind of normal operations and 2 months before they had fully restored normal operations. And then we had the Colonial Pipeline attack, which was a ransomware gang that attacked their business systems. It ended up shutting down the pipeline, which supplies the eastern seaboard of the United States with petroleum products for multiple days. There were long lines of gas. If you lived on the East Coast, you might remember people lining up to buy gas for multiple days. Now that was a ransomware gang, but it has nation-state level cover from Russia since they don't go and arrest their criminal gangs, so it has nation-state cover. These are both, these are examples of the kind of thing that we could see if we were engaged in active warfare with these kinds of, with nation-state level peers and they were launching cyber attacks on our systems. As we get more and more sophisticated in what cyber attackers could do with cyber level weapons, and if we don't improve our defenses on the cyber front, we could see these kinds of things more frequently. So increasingly hostile world, more and more complicated systems, more and more connectivity in our systems, increasing sophistication in cyber attackers on those complex systems. So just paying attention to efficiency is going to lead to more and more complicated negative consequences if we don't change what we're doing. So why are our cyber systems, so drilling down on the cyber piece, why are our systems vulnerable? So here is data from open source projects. I'm highlighting this data in no way to imply that open source systems are more vulnerable than non-open source systems. I'm highlighting this data because open source systems are available for scrutiny, so we can get data from these open source systems as a proxy for what non-open source systems might be. It's my hypothesis. We can speculate that closed source systems might be more vulnerable than non-open source systems. So the horizontal axis here is time. The vertical axis is percentage. This is data from the Synopsys annual report on open source security and risks. So and this is data compiled from across basically all industry. The list of industries it comes from is quite impressive. So the lighter blue color is the percentage of code in the code bases the top color, what color is that? Darker blue color is the percentage of code in these code bases that contains open source across many, many industries. It's 96% of the code bases contain open source. So the takeaway is that most industry is using open source code. The lighter blue color is the percentage of code in those code bases that is open source, and that's 77%. So not only is most industry using open source at all, they are using a lot of open source code. The yellow code is the percentage of code bases that contain at least one vulnerability, so that's 84%. And then the dark red is containing high-risk vulnerability. So a lot of code bases contain at least one high-risk vulnerability. So part of the reason why our systems are vulnerable is because they have high-risk vulnerabilities in them. It's also the case if you look at the MITRE CVE vulnerability enumerations, we publish vulnerabilities and we fix those vulnerabilities, but those vulnerabilities are not comprehensive, right? You list a vulnerability, but in the neighborhood around that vulnerability, there are many other vulnerabilities, right? We need to fix all the vulnerabilities in the neighborhood of the published vulnerabilities, not just exactly the published vulnerability. And those software vulnerabilities, it could be okay, but are people actually using those vulnerabilities to hack in? And this report from the Mandiant M Trends 2024 shows that, yes, people are actually using those vulnerabilities to create exploits, to hack in, to do their nefarious things. It's not just social engineering, it's actually the vulnerabilities in code that are being used. In fact, exploits are the most common way to break in. We need to fix phishing, we need to fix all sorts of other things too, but fixing hacked vulnerabilities is a really important priority. Then we have the fact that a lot of our software is maintained by lone heroes problem or opportunity. So I want to talk about the XE compression, the XE utilities library problem. So we had Lassie Collin, who was thanklessly or thankfully maintaining the XE compression utilities library for a really long time. And then he was convinced to hand over control of this very, very important library to Jia Tan by a collection of 5 other GitHub users who had complained or thanked him for his long-time service and pointed out that it was taking a long time for him to approve patches. And there was this other person, Jia Tan, who was very polite and very helpful and was doing a good job of offering useful suggestions. And so after about a year, Lassie turned over control of the XE utilities library to Jia Tan, who then proceeded to make more updates. It turned out that Jia Tan wasn't, as he appeared to be, someone from China who was helpfully making suggestions. It turned out he was some Russian guy, or maybe actually a collection of Russian guys working for nefarious purposes. It was identified by Andre Friend, who was a true hero. He maintains the Postgres SQL library, and he was unhappy with a 500 millisecond slowdown in his library. And in his spare time, he went to track down why his SQL library was going a little bit slower than he wanted. And he found that Jia Tan had actually inserted a backdoor in the XZ util compression library, and that there was a shell in that library. Of course, there shouldn't be a shell in a compression library, and that this was not yet in the main Red Hat distribution library, but it was very, very close to being in the main Linux distribution library, which would have meant that Jia and whoever Jia actually was, whatever organization Jia actually worked for, would have had root access to any Linux Red Hat distribution on the planet. Right? That would have made the SolarWinds compromise look like peanuts, basically. And we owe the security of that main distribution to Andres Friend in his spare time, tracking down a 500 millisecond slowdown. Right? The security of our system is of like massive amount of really important worldwide software to this person. You know, he's a true hero. You know, like we should really thank him. But like, why do we have much of the world's security due to people like that? So our software systems are vulnerable, way more vulnerable than they should be. We have a massive amount of technical debt. It's like this iceberg under the covers, under the sea line, but it's kind of worse than that because it's not just waiting as a natural disaster that will come get us, you know, that will be there, that we could run into at some point. It's like a sharkberg that is coming to get us, right? Because we have adversaries that are out to get us for real, right? And so we need to figure out how to change our practices and change what we're doing so that our systems are more secure and more safe in the face of global pandemics, in the face of natural disasters, in the face of global conflicts, where we have hackers that are not just waiting passively for our systems to crash into the icebergs, but where there are hackers that are trying to actively drive our systems into these adverse conditions. And part of what I'm here to do is to, you know, call to action for you and this research community, which contributes really important research to this area, to help us figure out how to build our systems to be more resilient, to not just be super efficient. Efficiency is really important, but so is resiliency in the face of the increasingly hostile world. How can we take one of these really complex, mega complex systems and figure out where is it vulnerable? How could we have looked at the Falcon system and figured out a syntax error could bring down Delta Airlines? How could we figure out how to cold start the internet? What if some hacker took down the internet? Could we restart it? How could we restart it? What would it take to restart? How could a hacker take it down? Is that a realistic prospect or is that completely ridiculous? Like, those are questions that you guys and your skills could potentially help us answer. What are other questions in that space that we should be thinking about? Those are questions that are super important in this new hostile environment that we are unfortunately living in today. We do have, imagining this world where our systems are not that vulnerable. We actually have some answers, right? We are currently accepting a huge amount of risk in our software systems. We're just waiting for our systems to be hacked and fixing them after they've been hacked, paying billions of dollars in remediation after the system's hacked. Like, what if we spent that money in advance building systems that are much harder to hack into? What would that look like? We actually know a lot about how to build systems that are more resilient already, that are much more likely to do what they're supposed to, and not do what they're not supposed to, using techniques called formal methods. Now, I'm not saying formal methods is a silver bullet that will fix all of these problems. No way. But formal methods can fix some of these problems today. We're just choosing not to use them for a variety of reasons, right? We have a lot of people who are in denial who think that hacking and cybersecurity is not really a big problem. We have other people who think that we don't know how to do anything about it. But I would argue, and I have been arguing today, that it is a big problem. And I'm going to argue in the next bunch of slides that we actually know how to do something about it. So we need to do research to solve more problems that I was just talking to you about, and we need to take what we already know how to do and start applying those tools more seriously. And that's what I'm going to talk about in the next bunch, in the next few minutes. Okay, so in terms of what we already know how to do, and why do I think we already know how to do something with those techniques, I want to talk to you a little bit about the HACMS program. So HACMS is a program that DARPA ran from 2012 to 2016. And it was taking this hypothesis that formal methods as they existed in 2012 were actually ready for prime time to deploy on militarily relevant systems to make it much harder to hack into. And so what HACMS did was start out with a system like, well, the unmanned little bird, which is shown here in the picture, and started with a red team saying, okay, can you hack into the system as is? And the answer to that was yes. Red team could hack in and take over remote control of the unmanned little bird. The Boeing engineers were a little surprised. No one else was particularly surprised. Then formal methods researchers got involved and taught the Boeing aviation engineers how to use formal methods-based techniques. And then the red team got to try again. And then the red team could not hack in and take over control. At the end of the program, the red team was given root access on a partition in the helicopter. And they were charged with taking over the helicopter, breaking out of the partition, disrupting the operation of the helicopter while it was in flight with 2 test pilots on board. Not only were the test pilots okay, they survived, they couldn't tell that they were flying in the high assurance version of the helicopter instead of the unaltered version of the helicopter. So the performance was fine. And the red team couldn't disrupt the operation of the helicopter. So performance and resiliency. HACMS then led to a number of other programs to work on making formal methods easier to use, more effective, more efficient, applicable at a bunch of different domains. So what was the secret sauce in HACMS? So the chart on the left there is the architecture of the unmanned little bird. It's still quite a simple system. There are 2 computers, the flight control computer and the mission computer. The flight control computer runs an RTOS that manages the flight control. The mission computer runs a kernel, and on top of that runs a Linux installation that has the camera software. Then there's an authentication system, and then a flight communication system that talks to the flight computer. There's a Wi-Fi communication. The red team was given root access in the Linux partition. When it, in phase 3, they were able to demonstrate that they could be in the Linux partition. They could overwrite the key and take over control. That's all without the formal methods piece. With formal methods, we replaced the kernel with SEL4, which is a fully verified to be functionally correct kernel. We did an architectural analysis in AADL that proved that there was only one way to communicate with the flight control computer. And that communication channel was always authenticated and encrypted, so bad guys cannot communicate with the system. We used verified parsing. So verified parsing by itself, if you just don't write parsers by hand, you vastly increase the security of the system. The SEL4 secure kernel is what guaranteed the separation between the partition where the bad guy's code was and the rest of the system. That's what the lives of the pilots rested on. That fully verified kernel did its job. Right. Amazon Web Services really took the lessons of HACMs to heart. Byron Cook went to Amazon and figured he had about a year to demonstrate the value of formal methods. He picked 5 projects of using formal methods and figured if one of them succeeded, he would keep his job. All 5 of them turned into grand slams. He's now a very high-ranking vice president at Amazon. We also now have him 20% time at DARPA as a program manager. One of the things they did at Amazon is they had the SSL, simple storage system, which is it's a simple storage system, but it's not simple, right? It stores like a million objects a second, and it has like 30 different simple processes that are doing different kinds of things, updating the store. And they had some kind of bug in the system. They knew they had the bug and they couldn't find it. They tried over and over and over again to try to fix this bug. They had some process that was going along and cleaning up the bug after the fact, so it wasn't majorly affecting the system, but it interfered with their ability to update the system because of this recurring bug. Eventually, they gave up trying to fix the bug, and instead they tried to prove the system functionally correct, which they did. And in the process of figuring out how to prove the system functionally correct, they found the bug, and they fixed the bug. And now they can make new changes to the code with much more confidence, because every time they go and change the code, they update the proof, and they prove that the new code is fully functionally correct. And that allows them to make new changes much faster than they previously could, because they don't have to go through this massively long testing cycle to gain enough confidence to make changes to this very, very complicated system that they can't afford to break because it's so important to the company. Instead, they prove it correct in a shorter period of time, and that gives them the confidence to be able to deploy the changes. And that allows them to make efficiency changes to the code that they wouldn't ever have been able to make before. So their experience at Amazon Web Services using these formal methods-based approaches is that after that initial learning curve, using formal methods has allowed them to produce systems that are not only more secure, which was the original goal, but also more efficient, more cost-effective, and at a better schedule. So like the program manager's dream, right? More secure, better cost, better schedule, more efficient. At our request, they've written multiple blog posts detailing their experiences at formal methods at Amazon. So when I talk about formal methods and trying to convince people to take a second look at actually using formal methods, they leap to the conclusion that I am talking about full functional correctness, like what I was just talking about with the SSL, simple storage, SSS, which is not the acronym Amazon uses, at Amazon, or about SEL4. That is one kind of formal methods. But in fact, formal methods is an umbrella term that has full functional correctness at one end, but at the other end is things like a sound type system or a memory-safe language, everything in between. Right? Anything that you use in your system to give you guarantees about what your system will do, and perhaps more importantly, what your system will not do, is an example of a formal methods-based technology. And they are all important pieces of making sure our systems do what they're supposed to and don't do what they're not supposed to. Low-hanging fruit is not writing parsers by hand. Something like 80% of the MITRE CVEs are related to buggy parsers. So if we could just stop writing parsers by hand and use parser generators, machine check parser generators, that could by itself dramatically improve the floor of our systems. Also using a memory-safe language, right? That also, memory safety errors, parsing errors, the vast majority of the flaws in our systems that let hackers get in and take over control are related to those two kinds of flaws. So just those two things, those are like at the low end of the formal method spectrum, but just those two things would dramatically make our systems more resilient, and that could go a long way towards moving towards less attackable systems. So some of the things that DARPA has done after HACMs, SafeDocs, addressing that parser piece, right? Older technology in parsers is the language, how expressive the parser can be. Context-free grammar is maybe not as expressive as they need to be. SafeDocs addressed very expressive parser languages where you can express dependencies, where you could read a number and then say, well, the next sequence has to be the length of that number in parser combinator languages. So when you're writing the grammar for the parser language, it feels like you're writing a program to do the parsing, even though you're actually writing a declarative specification of what that format needs to be. This program has led to a number of open source infrastructure for doing parsing, and we're working on transitioning this technology as broadly as possible. Then we don't have to deal with only greenfield coding projects, right? There's trillions of lines of code out there that is the problem. So we need to be able to deal with rewriting existing code as well. So the AMP and vSpells program are about applying technology to existing code bases. The AMP program is about existing code bases where you don't have the source code. You only have the binary code, which shockingly the US government, the US DoD, has a lot of this, where we only have the binary, but we know there's a problem in the binary, and we need to fix the binary. And so AMP, the concept behind AMP is you take the binary and you decompile it up to source code where you have the patch in the source code. Can you guide the decompilation process to match source code for the patch and then compile it back down to the binary in a way that you guarantee along the process that you haven't corrupted the rest of the binary, so it's going to still do exactly what you want it to do, and you haven't changed the performance. And this program made a ton of progress in the decompilation piece and in performance guarantees during that recompilation process, with a lot of really cool papers coming out in PLDI forum, for example. Then vSpells is you have a mass of really horrible spaghetti code, and you need to rewrite it. vSpells is about helping you understand your really horrible spaghetti code. For example, you have a handwritten parser which interleaves a whole bunch of processing, and you want to identify the parsing piece, extract the parsing piece, rewrite it, perhaps from a generated parser, from a high-level grammar specification, and compile it back down. Or you want to do crypto modernization, so you could have a post-quantum crypto algorithm instead of a pre-quantum crypto algorithm. So vSpells is in phase 3 right now, and it is applying the tools that it developed in phases 1 and 2 to exactly that, using crypto modernization and parser modernization as the test examples. Then here we are working on 3 programs. Provers is about, you already have a proof of a code that it's fully verified, for example, and now you update the code. What do you do with the proof? Can you automatically update the proof as well? There is preliminary evidence from work that Gawa did with Amazon that you can, in fact, automatically update the proof most of the time. They had a project with, I think it was SSL, where they had a year worth of updates to a proof, updates to a code base, and they had on the order of like 995 updates to that code base, and in all but 3 of the cases, they were able to automatically update the proof to keep it in sync with the updates to the code that did. So you didn't need to bring the proof engineer back. When an engineer made updates to C code, you could just update the proof automatically. The Provers program is leveraging a lot of machine learning techniques to be able to automatically keep that proof in sync as you make updates to the code base. Then the ARCOS program is about authorities to operate. In the military, in the DoD, when you want to put a system into operational use, you have to get an authority to operate. And that authority to, excuse me. That authority to operate is well-intentioned. It's designed to make sure that you have configured the system properly, that you haven't made any stupid mistakes, but it is a process-based process. So it is designed to, like, were the people trained appropriately? Did they go through all the steps appropriately? Did they use the right versions and things like that? It is enormously paperwork intensive. The ATO cases sometimes have like 2,000 pages worth of paperwork, and it can take 9 months to generate all the paperwork. And you get your certificate, and you're like, yes, I can now go use my new system. And then you're like, oh, but there's a bug in that version. You're like, it's going to take me 9 months to generate the paperwork again. I'm going to ignore the fact that I have a severe software vulnerability in that system. So like it entrenches bad software in the system because of the process. Like you wait to make fixes in batches as a result. So ARCOS is about, how about we automatically generate all the paperwork instead of having a process-based process to give us confidence that our system is good from a security perspective? How about we have an artifact-based, formal method-based process that is derived from the software itself that says, our system is configured properly, it's running the right software, it's in a good configuration, that we could regenerate on demand. So we could do this in days instead of years, and so that we can constantly have the system in a good state. And then EBOS is about using software bill of materials, but again, generating that from the artifacts. And the idea here is that once you have a bug that is known public, could you go back and use the enhanced SBOM to be able to find what of my software is actually vulnerable to this bug, and where are the vulnerabilities, and could I automatically patch the software within a day instead of within months or years, so that we can remove vulnerabilities really, really fast. Then we have Tractor. So we talked about how we have billions or perhaps trillions of lines of code in non-memory safe languages, C, C++. And we have Rust, which is a language with no overhead, runtime overhead, that is memory safe. But rewriting code from C into Rust is non-trivial. And we have, like, Google has committed to using Rust instead of C, but they're still writing more C than they're writing in Rust, even with that commitment. Could we, like, large language models are fantastic at translation, right? Could we automatically rewrite C, C++ into idiomatic memory-safe Rust? So not take it and package it up with unsafe, right? That hasn't accomplished anything. Could we do that? That's the hypothesis behind Tractor. We're starting with single-threaded Rust, single-threaded C. If we work single-threaded C, next phase is multi-threaded C. That's all that's funded currently, or allowed for currently. But if that works, could we go on to C++? That's the vision of Tractor. Could terribly fail, right? DARPA is about high-risk, high-reward research. But if we could do that, that could change the world, right? That's the vision of DARPA kind of things, right? Like, I don't know if it could work or not. There's a little bit of a basis of confidence. If it could work, it could change the world. This program was wildly subscribed, right? We got massive numbers of people interested, massive numbers at Proposers Day, massive numbers of proposals. It is just now kicking off. So fingers crossed, the researchers on this program are brilliant and they actually solve this problem. Because if we could eliminate C and C++, well, the program is just going to do C. That would be amazing. CPM is about automatically rewriting code into small compartments. So instead of having one big code base or one big code all running at the same privilege level, could we divide it up into little pieces that run in different privilege compartments and have those different privilege compartments separated with maybe hardware level protections, so that if an invader gets into one compartment, it doesn't automatically get into the whole compartment and get the privilege of the entire system. And that one is phase 1, just started. Okay, then AICC. So AICC is, again, looking at those large language models and how amazing those large language models are. The premise of AICC is, can we take the amazing power of large language models and marry it with cyber reasoning systems, put them together to build an AI-enabled agent that could automatically find and fix vulnerabilities in open source software? Starting with, again, the premise of, like, we have a massive amount of software that is running our critical infrastructure. That software is incredibly vulnerable, like the Colonial Pipeline. That's critical infrastructure software vulnerable to a hacking attack. If we need to fix that software super fast because we are exposed to adversary, where there's, like, armed conflict that's possible, if we needed to fix all that software super fast, how could we do it? Like, the only possible way is if we could create agents that could go fix all that software. Obviously, we don't have the authorities to do that right now, but if we were in an armed conflict, those authorities might change. Could we create AI-enabled agents that could just go and fix all that software? Right now, we don't have the technology, but could we have that technology? What if we paired AI-enabled agents with cyber reasoning systems? Could they go find and create patches for that software? That's the question behind the AI Saber Challenge. This is a competition. The semifinals happened at Black Hat in August of last year. The finals will be at Black Hat this next year. The semifinal top 7 teams each got $2 million. The final, the first place team will get 4, the second place team 3, the third place team $1.5 million. This is a competition that's in partnership with Anthropic, OpenAI, Google, Microsoft, the Linux Foundation, and the Open Source Security Foundation. In the semifinals, there were 42 teams that actually submitted cyber reasoning systems to compete. The competition, the projects that they competed on, there were 5 challenge projects: the Linux kernel, Jenkins, Nginx, SQLite 3, and Tika. The team that's running the competition created synthetic vulnerabilities that they planted in those 5 challenge projects. There were something like 60-some vulnerabilities that were planted. The teams found 22 unique of those planted vulnerabilities and 1 real 0-day. They patched 15 of them. So I think finding the vulnerabilities was exciting. Patching 15 of them, game-changing. Right? We were super excited about these results. Like a month later, I think Google, Project Zero, was super excited about their system finding a vulnerability. I'm like, we found 22 of them 2 months earlier, right? But the patching is the game-changing, the super game-changing piece. Like the ability to patch vulnerabilities is going to be game-changing. The finals is going to be in August. We are structuring the finals competition so that if the teams are successful, transitioning from the competition format to real world fixing vulnerabilities will be relatively small. So there will be opportunities to find real 0 days aplenty, and we're hoping that that's what comes out. Of course, we don't know. It's a competition. Again, it could fail. They could not do as well. We will see. But we are hoping that this capability will transition from the competition to real world relatively smoothly. We were a little surprised in talking to infrastructure owners. We thought that they would be super hesitant about applying this kind of technology in the world. Like, we're not going to go apply something that an AI wrote as opposed to a human. Their reaction was more like, oh, thank God. We know we have so many vulnerabilities and we are such risk, and we're told we have vulnerabilities all the time. So being told we have more vulnerabilities, we're drowning already. Like, we don't need to be drowned in 10 feet of water instead of in 2 feet of water. Like, we're drowning. But somebody coming with, here's how to fix it, is potentially, like, game-changing. We're also, like, thinking that the AI reasoning systems will be able to produce patches that will be, in the long run, indistinguishable from what a person would be able to produce. Like, that's not what we're doing in the competition per se, but like all of the documentation, all of the reports, the system will be able to do just as good a job. So we will see, and maybe that's a DARPA-like overreach, but that's what we're aiming for. We live in interesting AI times, right? Like I was just talking about AI system being able to produce patches. AI systems producing exploits. The analyses that the foundation model companies are producing right now are saying, like, no, they're not going to do that. They can't do that. Low risk for AI systems producing exploits. Nothing to see here. Go look somewhere else. I would love your opinion on, is that's true today, but not likely to be true in 6 months. That's true today, not likely to be true in the future. Like, what's your opinion on the state-of-the-art, long-term balance between offensive and defense as AI agents become more powerful? Like, currently, AI agents are pretty poor, right? The ability to string correct actions into long sequences of actions, they're not very good at that right now because of successive failures. They have to do many things in a row that don't fail to be as successful as an AI agent. Is that going to be true long-term? Is the fact that the current reporting from foundation model companies say exploits not really a thing that AI agents can do? Is that because they don't have enough training data? We just need to get them, they just need to be supplied with appropriate training data, and nefarious agents will do that? Or is that just actually a hard problem because undecidability, because it's a combinatorial problem, and combinatorics are still going to be really hard no matter like how good you are at AGI? I'd love your assessment long-term. So if you have an opinion about that, come talk to me later. And then I'm going to leave time for questions. So some of what I've talked to you about right now is long-term research, super high risk, lots of possibility for failure. But some of what I've talked to you about, the HACM's work, the SafeDocs work, the AMP work, the ARCOS work, that is work that DARPA has proven our technical hypothesis. And we need to get that much more broadly used across the DoD like yesterday, right? We have transitioned a lot of that technology to individual programs, individual systems across the DoD, but like to 23 different individual sort of recipients across the DoD. But the DoD has thousands of systems, right? That transition isn't broad enough. So my office has taken on the goal of transitioning those technologies to the entire defense industrial base. Yes, that is an insane goal. And so we've been doing a number of activities to try to increase the rate of transition of that technology. We've done a number of things to increase that transition. We convened roundtable discussions with the defense industrial base, with the R&E, with acquisitions, part of the Pentagon, with DOT&E, getting those two groups together to talk to each other. We've had really interesting exchanges where, like, the DIB says, we can't transition the technology because there's not a requirement. ANS says they can't require it because the DIB can't do it. It's like, talk to each other. Some of the DIB is like, we're doing this already, we just are doing it on our own money because we can't be paid for it because there's not a requirement. Other parts of the DIB is like, we would do it if there was a requirement so we could get paid for it. Other parts of the DIB is like, what are you talking about? Can I pay somebody to do this for me? Other parts of the DIB is like, could I pay somebody to do this if there was, and other parts of like the companies that have this capability is like, we would be happy to do this if someone would pay for us to do this. So like there's a market creation problem here. And we are working very hard to get this market created. Part of like the talk that I'm giving you today is trying to like, it's not like you guys try to incentivize the creation of this market to explain why it's so important that we raise the standard of resilience of our systems. So we've been working with R&E and ANS and DOT&E to do this. We have been launching capstone projects across, we're going to launch 4 capstone projects across the DoD to be like HACMs, where we pick a system of military relevance to a service, we do a red team exercise to demonstrate its current level of vulnerability, we then do a cyber retrofit using formal methods, we document what we did, and use that to inform a best practices guide. We then do another red team exercise to demonstrate what the new vulnerability level is. We diff those two to show potentially that it improved its cyber profile, and we build that best practices guide. We're going to be incentivizing proposers to DARPA programs in the future to use resilient systems-based approaches. So there's an RFI on the street right now asking for feedback on that. So future BAAs, in addition to the technical merit, the cost realism, the benefit to the mission, there will be a resilient systems category which will evaluate future proposals to DARPA proposals across the entire agency on the resilience of the proposal. And then we will hold an open formal methods colloquium on June 17th, basically we've been giving this message to DIB primes, more or less, giving this message to the open public on June 17th. You're welcome to respond to that RFI by March 7th. Yeah, encourage you to imagine that world without software vulnerabilities and to think about how that might fit into your research proposal. And finally, encourage you to continue or to join us with working with DARPA, either by doing your research or by thinking about becoming a program manager, right? Everybody who comes to DARPA as a program manager has an expiration date on their badge. They have to leave. You have to be able to get a secret clearance, so that means you have to be a US citizen, sadly. You respond to a solicitation, so BAAs come out throughout the year, talk to a program manager about working with them on a smaller effort. DARPA Connect is a web resource that describes how to work with DARPA in much more detail than I can do right this second. It talks about the Hayomara Catechism, how to answer Hayomara Catechism questions. In contrast to NSF, where you lead with the technical merit and then talk about how the technical merit might impact society, DARPA, the first thing to do is how your research will impact national security, and then what the technical merit is. So you just switch those two things. You can sign up for the I2M mailing list to get information about new program managers and what we're doing, and attend the Resilient Systems Colloquium that I just talked about. And with that, I will stop and have 5 minutes for questions. Thank you very much for your time.
Let's thank our keynote. So for questions, please line up at the microphones. Thank you very much, Kathleen, for a great keynote speech. Maybe I start with one, and then we take a question from the audience as well. So you mentioned great investments in the projects to tackle important problems, and they have been very influential. So I guess my question is, what areas do you not see enough investment? What would be the program that does not exist that would address an important problem?
Yeah. well, I would love to get your guys' input on what you think doesn't exist. We are doing strategy right now. Every year, DARPA offices do a strategy assessment, which is looking over the horizon about what are we not doing that we should be doing. So like I'm in the middle of that right now. So in some sense, I would love to hear from you guys what we're not doing that you think we should be doing. So like I mentioned in the middle there, like these mega complex systems, how do we understand, like how could we have known that leaving out a field in the configuration 291 file was going to cause Delta Airlines to cancel 7,000 flights, right? How do you know like the small change here causes this big problem over there? Or how do we, if that's too hard, how do we architect systems so that that can't happen? Or like that understanding mega complex systems, like can we retroactively understand mega complex systems, or do we have to architect mega complex systems so that they're more resilient? Like that's something that I haven't, like I think there's something there, but I don't know what it is exactly. The balance of power between offensive and defensive cyber, is that going to change with AI, or how is that going to change with AI? That's something that I would really like to understand better.
Thank you.
Thanks, Wes Hardiker, USC ISI. I loved your whole talk about formal methods and how much better things could be. Looking into formal methods to do software security has been on my bucket list for quite a while now. And the problem is that everybody feels like that guy in Nebraska, right? You end up writing code. You even said a second ago that your biggest problem is technology transfer, even within the government systems that you have at least some oversight over. And so what I'm wondering is, if now that we've proven that there are better ways to do things and better ways to create architectures, how do we get everybody to do it when there's such a high overhead cost, right? That's always the DARPA hard problem. How do you do the tech transfer, right? Any insights there? I mean,
so we're definitely working on that part too. Like part of what Provers is trying to do is integrate formal methods into the normal developer tool chain. I think this is a place too where AI might, I'm sort of answering the research side instead of the process side, and I think there's answers across the whole spectrum. On the research side, I think that AI might actually be a game changer here, where, because code is a language, and proofs are a language, and specifications are a language, and it may be possible to interact with a specially trained language model where you talk to it and you create a formal specification by iterating, and maybe you can generate a simulator to play with the formal specification to validate that, yeah, no, that is actually what I meant, or no, that isn't what I meant, wait here, and get a specification that is close to what you mean, or is what you mean, and then generate the code, talk to the system and get it to generate code, and then get it to generate a proof, and prove that the code actually implements the specification, and close that loop, so that the person is basically always just talking in English, right? And playing with the simulator, so that people are getting to interact in human native forms, and the system is doing all the concretization into computer native forms, so that we end up with formally specified and formally proven code in a way that is the people get to do what people do best, and the computer gets to do what the computer does best. And I realize that's an over-the-horizon thing. That's not a today kind of a thing. But I don't think that's wildly implausible. I think that might actually be possible. And AI is not there yet, but this kind of domain where you get a closed-loop feedback form, where you can give feedback to the AI system that, yes, this is right, no, this is not right, is the place where AI systems can improve the fastest. And the improvement rate on AI systems where they can get that concrete feedback is unbelievably fast right now. In terms of getting the processes adopted, I think you have to convince people that they have a real problem. If you can convince people they have a real problem and it will solve their real problem, then I think you can get motion relatively quickly, which is what Byron was able to do at Amazon Web Services. So find an organization that has the vision to actually improve itself and has enough resources to actually do that.
Yeah, so if I could flip around everything you just said, that really means we need to get to the point where it's faster to do it that way in a provable way than it is not, so that people actually use it. It makes sense.
Yeah, well, and that's what's happening with the SSS, the simple software, the simple storage system at Amazon, right? Is they couldn't do it. And that's part of why I think Amazon was an early adopter, right? Because they had sufficient scale that they knew they couldn't do it using non-formal methods-based technology. And so they were open-minded enough, and they had a super compelling evangelist in Byron. They also hired like the world's supply of formal methods experts at that time, which is expanding a little bit now.
Let's take one last question.
Jeffrey Yao with New Jersey Institute of Technology. Thank you very much for the talk. I have a follow-up question on formal method. As we work on formal method, I noticed a challenge to, I think everyone agree, it's very hard to come up with a specification and formal theorems that we want to verify. It's even a philosophical problem that what is the intended behavior of the software? I wanted to learn if you have any thought on that.
Yeah, and I think that it depends a lot on, like some of them are easy, right? This is why like parsers, it's easy to come up with a specification. A compiler, it's easy to come up with a specification. A real-time operating system, like the SCL4 separation kernel, it's actually really hard to come up with a specification of SCL4. It was just sufficiently worthwhile that they did it anyway. Some libraries, it's not that hard to come up with. Like a word processor, super, super hard, right? So I think it's a case where you need to look at the specific example. Like, is it worth it coming up with a formal specification in this case, or is it not worth it? In many cases, it's not worth it. And this is part of what I meant on the chart, where there's a whole spectrum of use cases, and only try to come up with a formal specification for things where it's worthwhile doing that. In other cases, it's enough to do type safety or memory safety, or a weaker property, like in the little bird, like I want to guarantee that the only messages that are authenticated and signed can reach the flight control computer, right? So like think about like what is the threat model, what am I trying to guarantee, and what is worth reasoning about in the system, and do that. So it's not like everything, I'm like, please not take away that I'm saying everything needs to be proven fully functionally correct all the time. That is 100% not what I'm trying to say.
Thank you very much.
Let's thank our keynote speaker one last time.
And
Please don't go anywhere. We'll go to our award ceremony right away.
let me just thank you for all the really cool, amazing research that you do. It makes a huge difference. Thank you.